Hello there, welcome to a presentation on solving systems of linear equations with two unknowns. My name is Charles Wasfane Msipa. By the end of this presentation, you should be able to understand how you can go about solving, for example, this kind of a system of linear equations, which you can see these two are linear equations of lines, like we have it there, but they were having as a system two of them, whereby the solution, as we know, will represent the point of intersection of the two lines. So the method we're going to discuss here, you should be able to extend it to a system of equations where we've got three equations and the three unknowns. And that can also be extended to equations, any equations with any unknowns, like here we've got x1, x2, x3 up to xn. Now, let's look at the following system. We suppose we're given the system of equation which we've seen here, like showing here that we can solve the system by using the method of elimination. But the method we're going to discuss here is to try to arrive at an approach which is going to be seemingly very far away from the method of elimination. The method of elimination at the beginning is motivated by the fact that one of the earliest equations we meet at school is something like this: 2 times dash equals to 8, which we later see as 2x equals to 8 when we know how to work with algebraic expressions. So what the idea of elimination is, try to take a new problem here which has got two unknowns, reduce to a problem which has got one unknown, and solve simple like we do here. We would simply solve for x by dividing both sides by 2, which will definitely give us 4. So then what do we do with, how do we approach this? Then this is what we do for the method of elimination. So we've got two equations there. We've got two unknowns. What we know so far is to angle equation with one unknown. So what we do, we eliminate one variable. Like for example, I can choose that I will want to eliminate y. Then I'll be left with an equation which only involves x, which will be the type of equation which we saw before, which is 2x equals to 8. So what we do here, we choose coefficients in this way. We want to eliminate y, so we try to make, in the two equations, make the coefficients of y be the same and differ only by the same minus sign, so that we can create a 0 y. Then we are left with we are left with the coefficient of x equals to the right hand side. So this is what we're going to do. We multiply the first equation by a22 there, and multiply the second equation by a12. a22 is this coefficient here, and the a12 is that coefficient. So what we are going to get, we're going to get something like this. We're going to get a11 times a22 times x plus a22 plus a12 multiplied by y equals to b1 times a22. Similarly, we get this here. What is important is that we note that the coefficients of y here are the same, h1, but they differ only by this sign. So what we're going to do next, we're going to, first of all, we must understand that if we're given an equation, we multiply the whole equation by a factor, the solution does not change. So in the two cases, the solution for this system will not going to change by the fact that we multiply by a common factor like that. So the next thing, what you can do also, if we add these two equations, the solution is not going to change. So what we're going to do next is the following. We algebraically add the two equations. In other words, when we add here, we're going to get 0, and I'm not going to write 0 there. We're going to get 0, then it is 0 plus, and we notice here that there's a common factor x, so we take out x as a common factor. Then we get a11 times a22 minus a12 times a12 tab by x. And the right hand side will be b1 times a22 minus b2 times a1, according to these coefficients we've got here. So once we've done that, I think we can see now that we are ready here to make x the substitute formula. Remember, in this case, I just used the general, letters A11, that just to take the system in its most general way without focusing on particular coefficients. So then next thing will be, after adding, we got this. Then making X substitute formula is simple. It's the same approach we use to solve this equation, dividing both sides by 2. So we divide both sides by the quotient of X here, then we get that. So let's hold on there on that and then see how we can get Y. We'll do something basically a similar approach. Now that we know X, we need to now to determine Y. So what we do again here, we choose coefficients here to multiply with. The target again, since we're eliminating X, we're targeting that the coefficients of X in the two equations be the same and differ only by the line, the sign. So that's why we multiply here by minus. So then the first equation will be like that: A21 by A11 X minus A21 by A12 Y equals to minus A21 by B1. And the next equation will be multiplied by A11 throughout. Then the next thing, we do exactly the same thing, adding these two equations here, we land on this equality here. And then again here, we're back to our old equation, 2 times dash equals to 8, which we know that we'll solve by dividing both sides by 8 once we have learned manipulating algebraic expressions. Then this lends us that Y is equals to A11 by B2 minus A21 by B1 over this denominator. Now let's look in the overall what did we get in the two manipulations. This is what we get. Given equation, if you notice properly, you can rewind this presentation if you want. You will see that X was given in this form and Y is that. So in other words, we're saying if we're given a system of equations like this, we can use this approach to calculate the value of X and calculate the value of Y. We're going to check that whether it works later with an example. Then let's move on. Now we want to unpack now our results, which are these two here. We want to unpack our results, which are these two here. Now notice that A11, A12, A22, this matrix is made of the coefficients of our known this side. So I'll call it coefficient matrix. That's why I use the C there. This is a coefficient matrix. Now its determinant, which you already know how to compute, its determinant will be denoted this way, and that's the principal diagonal product, which is here, minus the secondary diagonal product, which is there. So as long as this answer here is different from 0, so we're safe, all these things will be defined. Now, if you look now careful at this expression, you will see that this expression here is exactly what we've got there, which is what? Which is the determinant of the coefficient matrix. Let's not worry about the numerator for now. And then similarly, here Y has got the same denominator and that. So what we're learning here is that X in a system of equations like this can come as a rational expression, whereby X and Y can come as a rational expression whereby both have got a common denominator, and the common denominator is the determinant of the coefficient matrix. Now let's proceed and see how we can unpack to understand this thing a bit easier. Looking at the numerator now, let's say for X, we can see here that we've got A22 and A12. A12, we know this is the position for A12. A22, we know this is the position for A22. We can see it from this coefficient matrix here. And then we're left with B1 and B2, and the B2 is basically a column vector there, which is we can take it as B1, B2, a column vector which is on the plane R2. So then we put it like that, then that's what that calculation is going to answer. So similarly, this is still a common denominator. Then here we've got A11 whose position is that, and the A21 whose position is that. And then we're left with B2 and B1, and we know is that column vector, then we put it there. Then there we could say now we've got a kind of a formula which simply tells us that the two unknowns here are actually rational expressions whereby the denominator is a common denominator and the numerator is a determinant also, which is made of, if you check what's happening here, we're looking for x, which actually in the equation belongs to this column. In the equation there belongs to the first column. So what we do, we take the independent terms on the right of the equation and they replace the coefficient of x, and then the coefficients of y remain, we retain them there. Then the new denominator be the common denominator, which is made of the coefficient matrix entry. And similarly in y, we're looking for y, which in the equation belongs to the second column there. Then that we replace with that column vector, put that, and then we retain the column vector made by the coefficients of x. Then that way we calculate the value of y. Then we have to now test this whether it works. Now before I go further, I would like to say this approach which we've looked at here, some of you might have met it before, maybe presented in a different way. This is what we usually call Cramer rule. So we sit there with the formula or the rule given a matrix as a equation like this of two unknowns would get x this way and that way. Now here is a system which we have looked at before and solved. And if I recall properly, x here is equals to 1 and y is equals to 3. We can test that. Let's say we pick the first equation. We pick the left hand side. The left hand side is 2x plus 2y, given that x is equals to 1 and y is equals to 3. So what we're going to do here, we're going to substitute and say it will be 2 by 1 plus 2 by 3. Sorry, I copied this. This is not a 2, this is a 3. 3 by 3. So 3 by 3 will give us 9 plus 2, that will give us 11. And that is exactly what is our right hand side. So this solution satisfies the first equation, but that's not enough. Then we come to the second equation. The left hand side again on the second equation. In other words, I'm in the process of checking whether this is really a solution. Then after that, we'll like to use this method and see whether we get the same solution. So what I'm going to get here now, the second equation says 2x plus 4y, given again that x is equals to 1 and the y is equals to 3. Now substituting, we get here 2 times 1 plus 4 times 3. 4 times 3 will give us a 12, and plus 2, that will be 14, and that is exactly our right hand side. So this is the solution to the equation. So now let's see whether this approach will also give us the same thing. So I think the easiest way to do now is to extract the matrix, the coefficient matrix, which is 2, 3, 2, 4. And calculating the determinant of C, that will be 2 times 4, which is 8, minus 6, which is 2 times 3. And that will be equals to 2. So now, so our x is going to be a rational expression whose denominator is 2. And also our y is going to be a rational expression whose denominator is 2. Now coming to the numerator, we follow what we've seen there. For x, we need the independent terms. For x column in the equation, we need independent terms. In this case, which is 11 and 14. 11 and 14. Then the rest we replace, we just take the coefficients, the 3, 4, 3, 4. Then this we got here as denominator is 2. Then for 11 and 4 we get 44 minus 14 times 3, which will be simply 3 times 4, which is 12, and 3 times 1. 3 times 1 is 3 plus 1 is 42. Then what we're getting here, we're getting 44 minus 42, which is simply 2 over 2, and then that is equals to 1. So that answer there is what we got before. Coming to y, we do the same thing. The column in the equation which is for y, we replace with independent terms. In this case, 11 and 14, and then take 2 and 2. Then this would be 28 minus 22 all over 2, which will give us a 6 over 2, and then that will give us a 3. So we can see that we are getting the same solution. So we can now say we're satisfied this is an approach which we can use to solve this type of system of linear equations. At this point, I think I've given an example, and I think the explanation is clear. If you are feeling a bit uneasy, run over the presentation again and come to the example. And once you feel comfortable, take your text and solve simple equations of this nature, two unknowns, and then try to think of how you can adopt this for an equation with three unknowns. I think if you can do some examples and solve equations with three unknowns, that will be enough for now, because when we get to equations involving many unknowns, like let's say 10 unknowns and so on, that will be time maybe we need our computers and try to see how we can program this approach and solve the equations numerically using the computer. Already such programs exist, but it's not enough to be satisfied with the program without understanding what exactly is happening in the background. Because understanding what's happening in the background is what's going to give you some ideas what you want to do if you want to adopt an approach to any other particular problem, which is not a problem with a standard procedure. Otherwise, at this stage, I would like to say thank you for listening. Enjoy your practice.